Breakfast, all of you? Lunch also? All of you had your lunch?
No, sir.
Only Vinayak is responding. What about others?
No, sir.
No, breakfast
No,
also?
sir.
Okay, we will have a breakfast now. The breakfast called crystallization. Very good breakfast it is. So, do you know crystallization? What is the meaning of crystallization?
Formation of crystals.
Formation of crystals, right? Very good. Ice cream. Formation of ice cream. Also, what? Crystallization. So, solids are forming from the liquid state. Liquids will convert into solids. You know that one, right? To take the definition here, it is a process of formation of solid by precipitating from solution. So when you precipitate the solution, you are going to get the solid crystals. Now here, this is the important point. This is the important point for us. In this process of crystallization occurs faster rate. Okay. So process of crystallization, that means from liquid state, that means solution state to, from solution state to solid state, the conversion is very, very fast. Then what happens, constant particles are arranged irregularly, due to which there is a fault in the crystal structure called defect. So the process of crystallization is very fast. So in this very fast process, what happened? The constituent particles will arrange irregularly in the crystal lattice. Because of this, what happened? Some defects will form. To understand very simple, I'm calling all of you. For example, just imagine if I call all of you to the ground for what? Prayer. So I call you within the 1-2 seconds, you have to come to the ground. If I say what happened, all of you come very fastly and you make a line with what happened? A defect line you can make. With a random order, you may make a queue line actually, isn't it? Why? Because you came suddenly into the ground, no? So that is the reason you can't settle down. So that is the reason what happens, you may form a line which is what happened having in order. Similarly, what happened, the process of crystallization is very fast in nature. That is the reason these constant particles like atoms, ions, molecules, they will arrange in the crystal lattice irregularly. That arrangement we are calling as a defect. I think everyone understood why the defect will takes place. My voice is audible to you?
Yes,
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, listen to class now. It changes the physical chemical properties of the crystalline solid. Because of this, what happened? Some properties like physical chemical properties will differ. Few properties only, not everything. Some properties will differ actually because of the defects. How many defects are there? There are what actually two types of defects. One is called point defect. Other is called line defect, isn't it? So what is point defect? Generally, if you observe what happened, point defect means irregularity, isn't it? The irregularity or deviation at a certain point. At certain point means what happened. For example, I will show in the next slide. Only write that one. You will get in the next slide. What is that one? You will understand that one in the next slide. What is line defect? If you observe what happened, line defect means irregularity you are observing or deviation you are observing entire the row. Entire the row is what missing. Point defect, what happened? Only one point is what happened missed here. Entire the row is missed. For example, in your classroom, one of the student is missed, absent. For example, in your class, what happened? That Tejas absent. Okay, that space will be now empty now. That will be called as a point defect. For example, line defect means entire the row. The girls row, what happened? Missed in the class. One of the row, second row is what? Missed. That is called what? line defect actually. You observe here what happened. Observe here this one. Observe here A B A B. This is the arrangement. Okay. Again B A B A correct arrangement. A B A B correct arrangement. B A B A correct arrangement. Similarly, here also you are getting some arrangement of crystal lattice. They are arranged like this. Okay. They are what correct order. Now, how to get the defect? Let me see how the defect will absorb. The defect absorb like this here. Now you see B is missed here. See the B is here missed. One of the points here missed here. Missed here. Now this is called what actually? Point defect actually. Now observe here in the line defect what happened? Defect in arrangement of constant particles. This is because of arrangement of constant particles. Some of the constant particles are missed here. Here in the case of line defect, entire this row. Once it is a, here it is. Entire this one is a column. We can call vertical. It is what happened. Vertical line. What happened here? Disappear. Defect in a complete row, isn't it? That is called what? Constant particle. So in whatever the constant particles are there here, that completely what disappear. So defect because of the disappearing of a row or column, whatever it may be, a horizontal line or vertical line like that. Defect because of the disappearing of a points actually. So in this way, point defect, line defect can be explainable. Next, defects. Point defect further differentiated like stoichiometric, non-stoichiometric, impurity defects. All these are what very important for examination point of view. Stoichiometric, non-stoichiometric, impurity. Whereas line defect is screw dislocation, edge dislocation. So this is not there in the syllabus. So leave it this one. This is not there. Line defect is not there in the syllabus. You can avoid that one. Screw and edge dislocations we don't have in the syllabus. Next, stoichiometric again classified into vacancy defect and interstitial defect. So this is the classification of a stoichiometric. Non-stoichiometric again metal excess, metal deficient, metal excess and metal deficient defects. And finally, what happened? Impurity defects. If you observe what happens, substitution and interstitial defects. We discuss in this class about this classification, point defects. All are what happened, very simple to understand, very easy also, and there are what little bit only. Very large information is not there. Very simple information we are discussing. Next, of all, only in our syllabus we have only point defect. We don't have the line defect is not there. We have to discuss about all these topics. The right mark we have to discuss. So this is not there. Line defect is not there. First of all, we'll see the vacancy defect. This one. We're discussing about this one. Vacancy defect under what? Stoichiometric point defects here. Okay, this we are discussing. Vacancy defect. Very simple to understand. Let me see. Vacancy defect. Now this is the arrangement of crystal lattice. This is NaCl. Example, you take NaCl. Minus is what? Cl. Plus is what here? Na. Okay. They are arranged like this. The correct manner actually. The correct manner they are arranged actually. Now, how do you get the defect? You observe here what happened? Plus here. Plus. You lost plus, you lost minus here. Now, some of the points, if you observe what happened, they disappear here. Here it is disappeared. And here it is disappeared. So you got a vacancy here. Empty space you got because of disappearing of some of the constant particles here. This is called what? Schottky defect. In examination, Schottky defect is what? Very, very, very important. They ask in examination, what is Schottky defect? Give suitable examples. It's very important. Just you remove one cation, one anion. Okay, that is actually simple Schottky defect. Examples you see: sodium chloride, potassium chloride, potassium bromide, rubidium chloride, cesium chloride, cesium bromide. Now, when you observe these examples, all are which group elements? Cations. All are comes under which group? Anybody?
First group.
First A group they are actually. So easily you can remember. Examples also. Why? Because in MCQ questions, following which can be taken as Schottky defect, following which is not a Schottky defect, like that they can ask. So that is the reason. Sodium, potassium, they're nothing first A group element, easily you can remember. In addition to this one, silver bromide also comes, but silver bromide will be in even in the Frankel defect also. So common it is. It will be in the Schottky and the Frankel defect. So this one is very important for us. Silver bromide also very, very important for us. Examples are completed here. Now, the defect caused by absence of equal number of cations and anions, isn't it? For example, if you lost one cation, one anion also will be lost together. Two cations, if you lost, two anions you have to remove for this one. Okay, that means electrical neutrality you have to maintain. Because if you lose only plus, what happened? You will going to have excess, what minus will be excess there. So in that case, what happened? You have to make electrical neutrality. That means the number of cations lost will be equal to number of anions in this one. The observed density of the crystal is lower than the expected here. So what happened? Once if it lose this cation and anion, their density is what happened? Decreases, isn't it? Because of loss of some mass. When you lose mass, what happened? Density definitely what happened? Decreases. Next, second type. Second type means this one. Interstitial. This one now we're going to go interstitial defect here. This is called what? Frankel defect. This is called what? Schottky defect. This is called what? Frankel defect. Let me see the Frankel defect now. In interstitial defect, what happens here? It is due to cation or anion, anything it is, that leaves their position and occupy what? Empty space. Wherever empty space is there, wherever interstitial site is there, wherever void is there, that space is occupied. Let me see this one. That is possible when the cation is relatively smaller. Okay. So for example, if you observe what happened, for example, this is the actually crystal lattice. Okay, now what is happening here? This is you are losing here. This is the part you are losing actually. Actually, this part is there. This one you are losing this part actually. Observe this one. You are losing this part. Cation losing here. Okay. Now that is occupying where in the void like this. Here it is occupying. So we are going to get Frankel defect here. Observe here. One of the cation moves from their position into where? Into what? Void actually, into empty space actually, isn't it? Into empty. Just a minute. Hello. Yeah. हाँ ओके ओके. तो क्या करना है इसको? हाँ वायर चेक कर दो. Now what is happening here? Cation moving from its position to where? Empty space called what? Void here. Now this is called what actually? Frankel defect or interstitial defect. Now only generally what happens? Cation will be dislocated here. Why? Because compared to the anion, this cation will have small size. So the small size can be easily arranged at here. They can be arranged at here actually here. Plus can be easily arranged here because minus is what? Large in size. No. So generally what happens? Cations will be dislocated into what here? Voids here. Generally that is taking place here. And because of this what happened? Density is not changing. Why? Because this cation you are not losing here. Only you are changing the position. The cation position you are changing only. You are changing only the position of the cation. So that is the reason density never changes in the interstitial defect. This is very important point. In Schottky defect, density will decreases because you are losing the ions or molecule or constant particle. But interstitial defect, what happened? You are not losing anything, but what is happening? Only you are changing the position only. So that is the reason density does not alter in this case. So dislocation of ions, mostly cation. Mostly cation because of small size. Cation generally will have small in size actually. From lattice point to where? Interstitial site. This is called what? Frankel defect. What are the examples we can take? Zinc sulfide, silver chloride, silver bromide, silver bromide here also we got. Common it is. It is there in the Schottky defect. It is now there in the Frankel defect also, isn't it? Silver generally produce what type of effects here? Interstitial defects. Frankel defect generally by the silver actually. In addition to this one, zinc sulfide. Next, we will see the impurity, third type here. Third type of where? Stoichiometric defect, third type, impurity defect here. Let me see here. Interstitial impurity defect. For example, we'll take stainless steel. Stainless steel means what happened? Iron plus carbon. One more, it is what? Substitutional impurity defect called what? Bronze. I will show something actually. Now let me see, this one is iron. All are what? Iron something. Okay, let me. All are what? Irons here. So what is happening? Carbon, which is a small size, accommodating where? In voids here. Carbon, I am accommodating in voids like this here. Carbon accommodating. Because of this, what happened? Iron is getting some strength, strongness it is getting. That is we are calling as what? Stainless steel, isn't it? So otherwise what happened? Adding some manganese also. Not only, just I take an example, carbon, rough iron, isn't it? Cast iron, pig iron we can call when you add some carbon into that. Stainless steel means we can add something manganese, something like that. Now what about substitutional impurity defect here? In this we are not adding here actually. We are not adding anything at the voids positions. We are not adding anything. What I am doing here, simply I am displacing one of the atom here and placing one more. For example, you take bronze means what? Anybody, what is the bronze? Brass or bronze? Composition of brass or bronze? Brass composition, bronze composition. Are you hearing? Copper and tin. Remaining, I think they are not listening to the class, I think.
Copper and tin.
Kiran? Kiran? Absent. Nishant? Absent. Let me check. Are you listening to the class?
Yes, sir. Yes, sir.
Samiksha?
Yes, sir.
Yes, sir.
Yes, sir.
Actually, when you observe the substitutional defect, in this substitutional impurity defect, actually all are copper only. All are actually copper only. It is also copper only. But what actually we done here, in place of copper, we have taken, isn't it, tin here. If it is what? Bronze, I have taken here tin. If it is brass, I have taken here zinc. Okay. So some of the constant particles, some of the metal atoms generally are replaced with other atoms where they're having some equal size. Otherwise, if they are not having equal size, what happens? Definitely we are going to get other defect. So here, what I mean to say is that here, some of the constant particles are replaced with other constant particles, right? That is called what? Substitutional impurity defect. Whereas that is interstitial impurity defect means what happened? In interstitial positions, in voids, what we are doing, we are placing some external elements. Because of this, what happened? That is getting strength. So these defects, by using these defects, what we are doing here, we are making the metals into strength here. So they are useful defects actually. This type of defects are what? Useful defects to make the metals more strengthier. We are changing their crystal structures actually, isn't it? So with this, what happened? I have completed stoichiometric defects, isn't it? Kiran is there? Is Kiran
No,
is
sir,
there?
he's not there.
No, absent. Parth? Parth is there? No. This part never submit the assignment. Does not respond to the class. How many times I told you it doesn't change. Now this defect changes the original property of the solid. Because of this defects, what happened? The properties will be changed here. Next. We take one of the examples. See, this is a sodium chloride crystal lattice. The crystal structure of sodium chloride it is. Now, strontium chloride impurity adding to the pure NaCl. This is the impurity we are adding. Strontium chloride we are adding to what? NaCl crystal, which is a pure one. This is a pure NaCl crystal. This one, what you are observing is a pure NaCl crystal, which has actually no defect. Now, what I am doing here, when you add strontium chloride impurity added to the pure NaCl crystal in which no defect is observed, as all the positions are occupied perfectly. Now, what happens? Let me see. What happens here? This is the sodium chloride. Previous one is a pure one. This one is a pure one. Now, what we are doing here in NaCl, this is the empty space, right? This is the empty space you are going to have. Vacant side or empty space you are having. Empty space it is. It is not void. It is empty space. Void is not here. It is void actually. This is called void, right? Next. Now what I am doing here, see, strontium occupied here. Understand? Strontium occupied here. So previous case you observe here what happened. This is a pure one. Where it is occupied? The position here. What is occupied here? Strontium plus 2 occupied this position. Na plus position. See. The strontium plus 2 occupied here, Na plus position. Now, you are getting a vacant site here, isn't it? This is the vacant site you are going to get. And here, impurity added where? Here, strontium plus 2, you got a vacant site here actually. Now, see, actually, what is the meaning of this one? Why you got vacant site here? Because, see, the charge, if you observe, strontium charge is how much here? Plus 2. Where sodium charge is how much here? Plus 1. That means, 1 strontium plus 2 is equal to how many sodiums it will be? 2 sodiums here. So if I dopes, if I what happen? Add an impurity called strontium chloride, strontium plus 2, it will take 2 sodium ion positions. Why? Because to balance the charge. Otherwise what happen? Balance never charge. Because here plus 2 is there, here plus 1 is there. Charge balance will not take place here. That is the reason 1 strontium plus 2 is equal to 2 sodium plus actually here, isn't it? That is, you need to remember compulsory. Small quantity of impurities added to ionic crystal during crystal process, some of the lattice positions are taken up by the impurities. So in the previous case, what you have taken? NaCl ionic crystal we have taken. To that, we are adding some impurity. What is the impurity we are adding? Strontium chloride. So take strontium plus 2. So, if molten NaCl containing small amount of strontium chloride is crystallized, some of the sodium positions are occupied by whom? Strontium plus 2 ions. Just now we discussed this one. You have seen the slide also. This is they are saying actually. Okay. Next, each strontium plus 2 ion replaces 2 Na plus. Why? Because to make the charge balance, isn't it? To make the charge balance, they take like this here. Fourth one of the Na plus ion is occupied by strontium plus 2 and other Na plus ion site remains vacant to maintain electrical neutrality. See here, you observe this slide here. So strontium is what happened? Occupied the position of what actually? Na plus here. Na plus. Now here it is a vacant site is formed. Why this vacant site is found? Because 1 strontium plus 2 means we have to remove how many Na plus? 2 Na plus. Already 1 Na plus I have removed here. 1 Na plus I have removed here. One more Na plus you have to remove in another. So here I have removed here. So that is the reason if I take, for example, if I add aluminum plus 3 impurity. So we have to make 3 vacant sites. In that, 1 will be occupied by the aluminum and 2 will be what? Vacant sites. Understood this one? The cation vacancy produced are equal to the number of strontium plus 2 ions introduced into the lattice here. This is about that topic. If the impurity occupies lattice site, point, it is called what? Lattice impurity. If impurity occupies what happen? Interstitial site, then it is called what? Interstitial impurity. That means what is the meaning of this one? Very simple. If impurity is occupying interstitial site here, then that is called interstitial impurity defect. If impurity is occupying the lattice point of the crystal here, then that is called what? Lattice impurity defect actually, isn't it? That they are saying this one. Nothing is actually. Lattice impurity means what happened? The atom, the metal constant particles are replaced here. Where in the interstitial impurity, what happened? They are added to the interstitial sites actually. Now, Schottky defect is what type of defect?
Stoichiometric defect.
Stoichiometric defect.
This?
Stoichiometric.
Very good. Stoichiometric defect. Addition of strontium chloride is to addition of strontium chloride to pure NaCl.
Impurity defect.
Impurity defect.
Yes. Addition of strontium chloride is what type of defect we are going to get? Definitely
Impurity defect.
not point defect. It is
Impurity defect.
After completion of the answer, you are giving the answer. Everything. Next, we take second part here. Non-stoichiometric defect. We have completed now stoichiometric defect. Now let me take a non-stoichiometric defect here. The compound does not follow the normal valency rules, then it is said to be non-stoichiometric compound. Not following valency rules here. What is the meaning of not following the valency rules here? See, I will explain with taking a beautiful example. This happens due to defects in the crystal due to either metal excess, metal deficiency. When I explain this one, you will understand this valency rule. So two types of defects we can take under non-stoichiometric defect. One is metal excess, other is what? Metal deficiency here. Let me take first of all what happened. Metal excess now. Metal excess defect. Let me take metal excess defect actually. This defect is due to the anion vacancies. So this point you need to remember because of anion vacancy, the vacancy because of anions. Let me see this one. Alkali metal halides show generally which examples we can take. Alkali metal halides like what? Lithium chlorides. Lithium is which element? Alkali metal. Okay, lithium chlorides, lithium bromide, sodium, rubidium. They will show cesium. They will show this type of effect. So I have taken what? Sodium. Sodium, potassium, lithium all comes under alkali metal, first tier group elements. Their halides we can take for this example here. So we take what? NaCl now. I will take an example called NaCl. Now I will take what here? NaCl crystal. The crystal is what actually? NaCl. This is made up by NaCl actually. Na plus Cl minus. Na plus Cl minus. Like this, it is crystal is made up on. Okay. Now, when crystals of NaCls are heated in atmosphere of sodium vapor, the sodium atoms are deposited on the surface of the crystal. So what happened actually? This is the NaCl crystal. Now you are heated in which atmosphere? Sodium. So around this surroundings, what you are having? Sodium. Surrounding of this crystal of NaCl, which you are having actually sodium you are having. So when you heat this one, what happened? The sodium atom, one sodium atom will deposit on the surface of the crystal like this. Okay. So when you heat, what happened? From the sodium vapor, one of the sodium will deposit on the surface of what? Sodium chloride crystal like this. Now because of this, what happens here? So whenever on the NaCl crystal, what happened? Sodium is deposited. Immediately what happened? One of the chloride ion, this is the chloride ion, one of the Cl minus will come to the surface like this here. Okay? Now because of this, what happens if you observe? Now when this Cl minus comes here, okay? Now what happens here? You are going to get like that. Now already sodium is there. Now from this Na plus is there, something what happens? Cl minus and Na plus something. Now here the Cl minus is there. No, this is coming where? On surface. This is coming where? On the surface like this. So it is coming as a Cl minus here. Now because of this, this will be empty, no? This site will be empty. No, you take as empty because this is coming here actually on the surface. Now this is anion. There is no cation. This is atom actually. So it is actually lose one electron. Now this sodium will lose one electron and forms Na plus. And this Na plus will come down here. So we are going to get like this Na plus and Cl minus. Again here Na plus and this is empty space Cl minus Na plus like this. Now this electron will shift into here. That I will show in the diagram 6. First of all, we will complete this one. The released electron diffuse into the lattice and occupy the anionic vacancy. This vacancy, how it is found? Why this vacancy is found? Because this Cl minus shifted to what? Surface. So one empty space what? Formed here. One empty lattice is formed here. From where? Anionic. So that anionic position occupied whom actually? Electron. Now here we are going to get electron. Okay, this is called what? F center generally we call this one. Okay, let me discuss that one further also. Now as a result, now the crystal has excess of sodium ion because you got sodium from where? Sodium vapor that is converted into Na plus ion, right? And then the chloride ions, when you compare with what happened, now Na plus ions will be more than the Cl minus. If you observe this one, you will get this one. See, here you observe here what how many chloride ions are there, you see. How many sodiums are there? 1, 2, 3. But how many chlorines are there here? 2 actually. This is coming from where? Sodium vapor actually. From the sodium vapor, we got one extra sodium here. So because of this, what happened? One, the Na plus ions are increased when you compare with what? Chloride ion. Therefore, it is called what? Metal excess defect. You got sodium is called metal here. So you got more sodiums here. That is the reason what happened. It's called metal excess defect. We can call this one. And the anionic site occupied by the unpaired electron, the single electron which is released by the sodium atom, that is called what? F center. F from what? Farbengenter is a scientist name. From him they taken what? F name. F center we can call. And they impart. So each element will give different color. When sodium chloride, if I take, this will give yellow color. If I take sodium, the color exhibited is called yellow color. See, now I will show by using a diagram. So what happened actually, you see, on the surface. On the surface, let me take here. This is a sodium and chloride crystal actually. So you are heating this one where? In the sodium vapor. So you are heating this one where? In the sodium vapor. So immediately what happens? Sodium is formed on the surface here. Now here, one of the chlorine is moving to where? On the surface like this. So you take that one. Here it is moving like this. One of the chlorine is moved here. Now this sodium is also lost one electron, forming what? Na plus here and releasing one electron. Now this Na plus will come here and this electron will move to where? Here like this. Okay, let me this chloride ion. Let me take this one actually. This is a diagram actually what we discussed. Next is the free electron which is formed from where? Sodium atom. Now because of this what happened? The sodium atoms will be excess when you compare with chloride ions. How you are getting, let me see, metal excess defect. Now you see this electron occupying where? For example, if this sodium is this chloride you are losing, this Cl is what? Coming to here. Coming here. Everything is here. This sodium chloride is coming to here actually. Now this is bit empty actually. It is getting what? Empty now. It is getting what? Empty now. Now this empty position occupied by whom? This free electron like this. Now because of this what happened? Sodium ions are more than the Cl minus. It is called what? Metal excess defect. The electron which is released from this sodium, isn't it? From this sodium occupying where? The empty space which is formed by the dislocation of the chloride into the surface is called what? This type of metal excess defect actually. And this center you are calling empty is called F center, Farbengenter center. Now you are getting electron here, no? That is the reason what happened. It will get conductance, more conductance it will get. The color results by the excitation of these electrons because you are having the free electron, no? Because of the free electron what happened? It absorbs the energy and come down into the ground state. It will release the energy in the form of visible light. Therefore, it will appear as a color actually. The color result by the excitation of these electrons when they absorb energy from the visible light falling on the crystal. On similar lines, if I take lithium chloride in the place of sodium chloride, if I take lithium chloride, what color you are going to get? The pink color. If I take what happened, potassium chloride, the color we are going to get violet color. In this way, what happened? We can explain the metal excess defects here. Metal excess defect is due to the presence of extra cation. I told you, no, more sodium plus ions we got here, isn't it? Next, we'll take zinc oxide is white in color. If I take zinc oxide in place of what sodium chloride, if I take what zinc oxide, we are getting white in color at room temperature. On heating, what happened? It turns into yellow color. That we'll discuss in the next slide. Why it turns into yellow color, everything we'll discuss in the next class. This side. So zinc oxide will convert into zinc plus 2 and half oxygen plus 2 Li. Otherwise, you write like zinc converting zinc oxide plus 2 O minus 2. Now what happened here? Zinc plus 2 plus 1 oxygen, and these 2 electrons losing from oxygen, you are getting 2 electrons like this. Now this you are going to get. Now there is an excess of zinc now in the crystal, and the formula will be zinc 1 plus X. Why? Now you observe here, I told you just now. Why it is non-stoichiometric defect? Why it is called non-stoichiometric defect? Now you observe here what happened. In this case, why it is called what? Non-stoichiometric defect. See, in the previous case, we got more sodiums when you compare with what? Chlorines here. Now, 1 sodium is extra. So, generally, we have to call sodium chloride. But 1 sodium is extra, no? That is the reason what happened. The number of, isn't it? Atoms, ions are not balancing them. So, that is the reason what we are calling non-stoichiometric defect. So, we have taken the definition, no? The previous slides we have taken a definition. Yeah. Because if the compound does not follow the normal valency rules, then we get non-stoichiometric compound. When we get not following the valency rules, see, there are more sodium ions are there when you compare with chloride. That means more positive charges are there when you compare with what? Negative charges. So valency rule, what happened here, not following, then we get the non-stoichiometric defects actually. All we discussed already. I'll move to next slide. Now we are discussing actually this one, no, zinc oxide. Zinc oxide. No? Let me take this zinc oxide with a suitable example now. In this type defect, oxide is heated in oxygen atmosphere. In the previous slide, what we have taken, sodium chloride we have taken, and we have heated sodium chloride in the atmosphere of sodium vapor. Now what we are doing, we are heating in the atmosphere of oxygen now. Okay, then cooling. After that, what happened? The conductivity decreases. This is because of, I will explain this one, why the conductivity decreases. In the previous case, conductance will increases. Now it is decreasing. Let me see the reason. This is because the dioxygen oxidizes some of the interstitial ions, and that subsequent removes interstitial electrons, that reducing electrical conductivity. I will explain this one by taking some diagrams here, these statements. Okay, everything will be easy. Now, what I am doing here, I have taken zinc oxide crystal. This is called zinc oxide crystals. So everywhere you are alternately you are going to see zinc plus 2 O minus 2, zinc plus 2 O minus 2, right? Next, on heating, what happens here? One of the O2 minus here. One of the O2 minus will convert into half O2 and these 2 electrons. Here we don't have any charge. Observe. The 2 electrons are released like this. So this reaction is taking place on heating. Next. Oxide ion is converting into oxygen now and releasing what happened? 2 electrons. See, oxide ion converting into oxygen, releasing what happened here? 2 electrons. This is happening now. You observe here what happened, you see? One of the oxygen, this one. You take this example, better because in the slide they have taken this one. Anything you can take, no problem. Now, oxide converting into oxygen. See, now this space, if you observe what happened, occupied whom actually? These 2 electrons. See, you have got a 2 electrons. You got a 2 electrons. Now, one of the oxide ion converting into oxygen like this and release 2 electrons, and the 2 electrons will taken by whom? Isn't it? Occupied by whom actually? the empty space here. Oxide empty space is occupied whom by 2 electrons, isn't it? This is happening. Now let me take next slide here. Now O2, again the O2 takes the 2 electron and converting into O2 minus. That means you take half O2. Again that oxygen, whatever it is converted, will again gain the 2 electron converting into O2 minus in the reduction process. This oxide ion return to their lattice sites, decreasing the electrical conductivity. This happens on cooling. So when you cool, what happen? When you cool, what happen? This oxygen again taking the 2 electrons and converting into again O2 minus. Okay, when you do cooling actually. So in cooling, what is happening? You are losing these electrons again. Again, the electrons are taken by whom? These all electrons are taken by whom again? This oxygen, isn't it? This oxygen is taking all these electrons here. Again, come back into what? O2 minus. So on cooling, this is losing what actually? Its conductivity. So this happens on cooling. Again, this is occupied. You observe here what happened. Occupied again. You observe here what happened. The 2 electrons are occupied whom? O minus 2. Okay. In this way, what happened? It is taking place on cooling actually. So yellow in color when hot and white when you cool that one, isn't it? Because of the electrons. The reason is because of the electrons actually. Oxide is coming back again. Whatever the oxide is coming back here actually. For examples, we can take for metal excess defect, cadmium oxide, iron oxide, Cr2O3. You can take remaining examples here. These are the remaining examples we can take. We'll take some questions here. Occupation of electrons in place of anion site is called. Which type of defect it is? Which type of site it is? Occupation of electrons in place of anion site is called what?
F center.
Yes, F center only. Electron, occupying of electron on anionic site, F center, very, very important. Many number of times this question was asked here. F center only it is. Heating the zinc oxide, which is white in color, turns into yellow by loss of what? Heating the zinc oxide, which is white actually, turns into yellow color by loss of what actually? Again, it's turning into yellow color. By loss of actually what happened? Electrons only, no?
Oxygen.
No, yes? That means electrons is losing, but happen? Oh, okay. This is sorry. It is what? Heating, no? Okay, not cooling actually. It is heating. Question is what heating, no? Okay. When you heat, what happen? You lose oxygen. See something like O minus 2. Last, what happened? Oxygen, half O2, plus what happened? Electron. So on heating, white convert like this here. Cooling, what happened? It lose electron. They given here what heating actually. They say what happened? Cooling, what happened? They lose electron. So we'll get electrons answer, right? Next, non-stoichiometric defect with metal deficiency. Now, this is the last one. Metal deficiency defect here. Metal deficiency defect here. There are many compounds which are difficult to prepare in the stoichiometric composition and contain less amount of the metal compared to the stoichiometric proportion. We are having here less amount here, less cations are available. In the previous case, more cations are available. You see here, actually the composition of iron oxide will be FeO, ferric oxide, ferrous oxide, sorry. It is Fe plus 2, ferrous oxide, but you are representing 0.95. That means it is having some deficiency. How much deficiency is having? 0.05 it is having. 0.05 it is having. The deficiency you are having how much here? 0.05 it is having. Now, actual composition of iron ranges from 0.93 to 95, but I have taken something 0.95. Okay, actually the composition varies because of the defect actually. In ferrous oxide crystals, some of the Fe plus 2 ions are missing here. Okay, they are replaced with what? Fe plus 3 ions. Okay, in a ferrous crystal, some of the Fe plus 2 cations are missing, and the loss of positive charge is made upon by the presence of required number of Fe plus 3 ions. If 3 Fe plus 2 ions are missing, for example, how many we have to take? 2 Fe plus 3. Why? Because 3 to the 6. Here 2 3 is 6 here. So if you lose 3 Fe plus 2 ions, 3 ferrous ions, how many ferric ions we have to add? 2 ferric ions, so that we have to maintain electrical neutrality. Now, positive ions are present in the metal deficiency defect actually. Positive ions are absent in the metal deficiency defect. See, where positive ions something, what happened? Cations. They are missing. When they are missing, what happened? Definitely positive ions are nothing but what? Metals only, no. Metals are nothing but called as a positive ions only. They are missing, therefore they are called metal deficiency defective. The extra negative charge in the lattice is balanced by the metal ion having higher positive charge. For example, Fe plus 2 is there. Now this you are balancing with what? Fe plus 3. Okay, that means what happened? With higher positive charge, we are balancing the whatever the extra charge we need actually. Type of defect is shown by metals which show variable oxidation state. Now all metals do not show. Whichever having show more than 2 oxidation state. For example, you have taken iron, no? Fe can show Fe plus 2 and Fe plus 3. Now we can take this for example here. You can't take zinc here. You can't take zinc. Why? Because zinc will show only one oxidation, that is what zinc plus 2. Can zinc plus 2, zinc will show non-stoichiometric defect of metal deficiency? No, metal deficiency never shown by zinc plus 2. Why? Because it will show only one oxidation state, that is zinc plus 2. Fe plus 2 plus 3 can show 10 plus 2 plus 4. Yes, it can 2 oxidation states. So whenever it is showing more than 2 oxidation states, that type of metals will show the metal deficiency defects here. So we have taken iron, we have taken vanadium, we have taken nickel, we have taken copper. Copper can show copper plus 1, copper plus 2. Nickel can show nickel plus 2, nickel plus 4. Vanadium can show vanadium plus 2, vanadium plus 3, vanadium plus 4 it can show. And already you know Fe plus 2 and Fe plus 3 they are showing actually. So these are the examples we can take for what? Metal deficiency defect here. So now let me take some example. Let me take some example for this one. Now it is a simple crystal not having any defect. It's a defectless crystal lattice of iron oxide, FeO. This is the structure of what actually? FeO. I'm writing here FeO. Okay, not having any defect here. Now in this case, what happened? How many Fe plus 2 ions are there? Total 10 Fe plus 2 ions are there. Total 10 Fe plus 2 ions are there. And same oxygens also same. 10 oxygens, 10 irons are there. Iron in the Fe plus 2, oxygen O minus 2. So 1:1 ratio it is formed. So it is a stoichiometric here. So it is a stoichiometric compound. Next, what is happening now here? Defects, metal deficiency defect you got here. You observe here what happened. This position is not Fe plus 2. It is Fe plus 3. This is Fe plus 3. Okay. Now, and remaining you have observed Fe plus 2, Fe plus 2, Fe plus 2. All are what happened? Fe plus 2, Fe plus 2 something. Now here also what? Fe plus 3. I told you in the next, this class only, in the last slide only, 3 Fe plus 2 is equal to how many Fe plus 3 here? 2 Fe plus 3. Okay. 3 ferrous ions are equal to 2 ferric ions. Right? 3 ferrous ions are equal to 2 ferric ions. Actually, it is Fe plus 2. Occupied by whom? Fe plus 3. Actually, it is what? Fe plus 2. Occupied by whom? Fe plus 3. Here it is empty space here. Why we need empty space? Because we have to vacate 3 Fe plus 2. Here also actually Fe plus 2 only. So when in the metal deficiency defect, what happened? We lost 3 Fe plus 2 ions. We have lost 3 Fe plus 2. One from here, and one from here. But we can't place 3 Fe plus 3. If I place 3 Fe plus 3, what happened? It gets total 9 positive charges. So 9 positive charges we are accommodating here is impossible. Why? Because you lost 6 positive charges. So we have to make only 9 positive charges, 6 positive charges only. So making 9 positive charges are impossible. So I have taken how many? 2 Fe plus 3 only I have taken. 2, 3, 6. Now 6 positive charges are balanced here. And 1 will be vacant here. This will be vacant. This will be vacant here. Isn't it? Because of this, what happened? There should be actually 10 iron ions, but actually in this, after defect, what happened? You got 7 plus 2 and 2 Fe plus 3. Now 1 iron is missing here. 1 iron is missing. And O minus 2 you are not changing. O minus 2 are 10 only. When it is pure state, the O minus 2 are how many? 10 only. But in the impure state, metal deficiency defect, what happened? 1 iron you are losing. Why you are losing 1 iron? Because the Fe plus 2 is occupied by the Fe plus 3. in which 3Fe plus 2 is equal to 2Fe plus 3. We have to balance what charges, not atoms here. So you are losing 3Fe plus 2, but you are placing 2Fe plus 3. So one of the Fe plus 2 is what getting vacant here. Therefore, you got deficiency on the metal ion. Therefore, you lose the last year. What happened? One of the metal. Therefore, it is called what? Metal deficiency defect. So there is one metal site vacant, isn't it? Indicating metal deficiency defect. Now we have to take this. How many ions are there? 0.93 to 0.95. For one oxygen, we are having not one oxygen. This is not correct. This is for pure state. Okay, no problem. In impure state, what we got? How many ions are there for one oxygen? From 0.93 to 0.95. When you take what average value, take average value, you will get like. Now this is called what? Metal deficiency defect. When are the defects observed in crystals? When the defects observed in the crystal? Anybody?
When the crystallization process is fast.
Whenever if you do the crystallization very fast, you can get the defects here. So if you want defects, I want something, what happened? Defect. What I have to do? I have to take the solid in the liquid solution and heat that one. We'll get the solution. Now after that, what you have to do? Immediately you have to cool that one. Immediately you have to decrease the temperature. So suddenly crystallization takes place. Now we get the defect. Defects are actually doesn't take place. We have to make that one to get some extra properties, to change the properties. See, for example, iron is very soft in nature. To make iron hard, what we are doing? We are making the defects into the crystals actually to get the hard nature for that one. It's about actually today's topic. With this, what happened? Solid state is completed. We don't have in the syllabus electrical properties. In a CBSE examinations, we don't have the electrical properties, right? So up to here only we have topics are there. But anyhow, I will make a video on the electrical properties on YouTube. I will post that one. So in for examination, when you are having examination on Tuesday, no?
Yes, sir.
Yes,
Tuesday
sir.
you are having exam. So until now, this topic is there in the examination. Definitely will get many number of questions from this one. In the defects you will get also. And like in Z deficiency of BCC, Z deficiency of what happened FCC, cubic lattice. Okay, you have to practice that one. Packing efficiency percentage, you have to practice 74%, 68%, 54%. These are all percentages of FCC. One is what? Cubic and BCC and FCC. All these packing efficiency and empty space. This number you need to remember compulsory in examinations of solid states actually. Any doubts you are having? Are you preparing for examination? Otherwise, simply writing. Are you preparing for examination? No preparations. What are the topics are there? Only 31 students are there today.